Uh, in ancient times, we used to send letters, but they were not sent in an open way. They were folded. We used wax seal and then used signet rings to stamp them. The ring gave authenticity, and the wax seal was all about privacy. It's a guarantee that no one could peek into the contents without leaving a trace. So we'll fast forward that for today. We use apps like WhatsApp and Signal. Their claimed end-to-end encryption says they protect our chats end-to-end. It's the same concept. The pattern is very clear. Whenever humans use to communicate with each other, they instinctively try to create ways that are privacy preserving. And in this AI era, we are entering into a new kind of communication. That is communicating with AI, right? And when you type a prompt or upload a data into a model or an AI system, you're not just talking to a software. You're talking to a persona, you're talking to an agent that interprets, that understands, and responds back your queries. And just like how you interact with people, you expect whatever your interaction with AI system is stays between you and them. But as engineers, we often forget that. We see AI systems as APIs, models, and pipelines. We tend to forget the persona or conversational partner aspect of AI systems. And due to that very instinct of developers, we often think about privacy as an afterthought. It's a secondary thing, or it's an optional thing for us. And it's not a design principle in any of these AI systems. So confidential AI is about changing that perspective, and it's not like a novel idea. It's been there since very long time. We use it on a regular basis in our chat applications, and we have used it in the past. So, but it's the same thing. It's the wax seal moment for the age of AI. And as Yaroslav introduced us, my name is T.A.Aziz. I'm pursuing my MBA from Indian Institute of Management. I also hold a bachelor's degree in computer science. I'm a software engineering manager in data and AI team. And there we are shaping the future of AI with open source. So I have with me.
Hello, I'm Navinya. I'm senior principal software engineer at Red Hat and data and AI team. I have been with Red Hat for 7+ years now. I have around 10 years of industry experience in IT industry. And I'm a frequent speaker, as Yaroslav mentioned. I usually speak at devcon.cz and other conferences and try to share knowledge, whatever I have. Yeah, back to you, Aman.
Thank you. So that brings us for today's topic, model-side confidential inference. Basically, what if your AI model could decrypt your data only at the last possible moment and inside its own memory? It never gets exposed anywhere outside of that thing. So I think before going to answer that question, let's do like a quick refresher on AI things, which may be important while you attend this session. So the AI thing was for years, like it has been around, and it was about classification and prediction. There were a set of images, labeling them as cat or dog, or sometimes cat and dog, right? So, but then the generative AI shift happened. It was based on the transformer architecture on a 2017 paper that titled with "Attention is all you need." From there, this wave of progress started. Basically, we use massive data sets and massive computational powers. And with scale, we saw some basically emergent abilities, and those appear at a certain scale for us. So when we talk about transformer architecture, it has two phases. One is training phase, that is like a very expensive, long-running, and needs a lot of data and takes time. There you train your model's weights and biases so that it could be used in your next phase, that is the inference phase. Inference is the portion where you type a prompt and model tries to generate tokens or words out of it based on your prompt. So this inference phase is quite fast and relatively computationally lower cost. But many organizations as of now are struggling with making it even faster, making it even cost effective, and also cost effective, as well as making it privacy preserving. So oftentimes you will get requests, like somebody in higher ups may ask you, we want to have these AI systems, but none of my chat should be visible by any of the developers or any of the monitoring systems or any of the logging systems, just because it contains relatively important data, confidential data, and how we can achieve that, right? So that is all about the inference. Then there are the agents and MCP. So AI agents are a chain of these inference calls or workflows of these inference calls, where these agents can actually plan, reason, and then execute multi-step tasks based on the prompts and chain of these prompts. And to manage these AI agents or communicate with AI agents, these follow some emerging technologies as model context protocol. You can think of it as a protocol that manages models' short-term memory. You can provide it with data, you can provide it with tool calls, you can provide it with your conversation history. That way it's aware of all the past things as well as what capabilities it has. That is kind of the refresher for the AI things. And we can talk about the problem that we are struggling with. So security folks, we are good at protecting our data in transit as well as data at rest, right? So TLS protects in transit things, disk encryption protects data at rest. As we talked about TLS and disk encryption, those are not enough for protecting AI pipelines. Once our prompt enters the AI stack, it's plain text everywhere. Whether you are using or it hits your API gateway where it's decrypted and logged. If you have a reverse proxy, it's seen there too. All of your logs, your monitoring systems, and your debuggers and auditing tools, they all capture these prompts. As well as the most important thing, the AI middleware, the AI frameworks, they also have access to these prompts. And that's where we want to have it in use encryption. So at every single one of these prompts, plain text exposure points, we want to ensure that it's not leaked and it gets encrypted throughout its journey. So as I talked about, in transit, at rest, but while inferencing, it's not encrypted. So that's how even some of ChatGPT chats were leaked and it was indexed on Google. So if you imagine having your private conversations with ChatGPT, and suddenly you get to see all your chats are available on Google, and everybody can read those things. So you definitely want to avoid such a thing for all like AI use cases. Yeah, I mean.
Cool. The idea here is basically, as Aman explained, how we can make sure that the decryption of the encrypted prompt happens only in a trusted memory space of the model and not anywhere else, as like there were few points of exposure that was mentioned by Aman. So the concept is simple. The user or client encrypts the prompt using OpenSSL encryption. Then the encrypted prompt travels across network. So here we are getting dual encryption. It's already on the network, it's already encrypted using TLS 1.3 protocol. Additionally, we are encrypting the prompt as well. So even if someone captures the network logs, he wouldn't be able to read anything. Then the prompt is decrypted inside the model's trusted memory space. What model does is it tokenizes, processes, and generates the output. Then it re-encrypts the response of the model. So even the response that is generated by model is not like exposed on even on the network or anywhere else, and only the user can decrypt the response of the model. Next slide, please. Yep. So now, why OpenSSL specifically for this use case? So as all of us heard in the session on first day, that 70% of the internet runs on OpenSSL. OpenSSL is a battle-tested library that helps to implement the complex encryption algorithms while abstracting away the implementation details. For this particular use case, what we have used is the AES 256 CBC encryption to encrypt the prompt data. OpenSSL is like widely available and provides interfaces for multiple languages and frameworks like Java, Python, and CPP. Next slide, please. So here I will give a brief overview of the architecture of the current application, the POC that we have developed. We can dive deeper once we see the demo. That will help you to connect with what all is happening correctly. But at high level, we have like a client application that users interact with. It's a Python application as of now, but it also provides an API server. So it interacts with the API server. In client, we have like a Python CLI application where users can type their prompt. Then there is a clear segregation of concerns. For example, if you can see the LLM encryption client box, what happens there is it only interacts with the client, takes the request, then passes on the request to encryption manager. So I have developed a Python client which uses PyCryptodome to do AES 256 CBC encryption. Then the encrypted prompt, and another important step that is happening here is a random initialization vector is initialized. So for every single question that you have, a new initialization vector would be sent along with the request. Using that initialization vector, the server can then decrypt the encrypted prompt. So what happens at Llama client HTTP level is it takes the encrypted prompt and initialization vector and does a base 64 encoding. And all of this is done on user's device. At this point, like nothing of the information has left like user device. Then the encrypted request, which contains prompt and initialization vector, is sent over the network. So we have, as I mentioned earlier, we have dual encryption. The prompt is encrypted as well as there is TLS encryption in place. The request is then goes to encrypted server. So we have modified the llama.cpp server for the POC purpose here to show that this is possible. Then we have Llama encryption server, which is like a modified version of Llama CPP. It decrypts the request using the initialization vector that was shared in the request. Another important thing that you need with initialization vector is the shared encryption key. For the POC purpose, we have like a static key hard-coded into client and server. But I will obviously share like how you can do this in production use. Then once it has decrypted the encrypted prompt using OpenSSL's AES-256 CBC encryption algorithm to decrypt that data. So it needs initialization vector and the shared key. Then it goes to llama.cpp's model, and here all the model will actually generate the response, do the inferencing part. Llama.cpp currently supports .gguf models, so you can download those models from Hugging Face for free and run it on your local machine. Next slide, please. So yeah, it's time for live demo. I hope you guys are excited. Cool. So what I'm doing here is I'm running a model, Llama 3.2 3 billion instruct model, download from Hugging Face, and I'm running it on my local machine. So I will start the server. The server model has been like modified to support encryption. So as you can see, it's pretty fast. The server has been started. Now on the client side, I will interact with the Python client using this particular question, like give me a brief overview about OpenSSL in 2 to 3 lines, and let's see what model has to say. So what happens in the background is the encryption is happening, the shared key is being sent over network, and since it's on all on local, it's pretty fast. So as you can see, the server sent encrypted response, but the client was able to interpret that and decrypt it back. And to prove that all of this is not a gimmick thing, like directly the LLM response that is being showed, I will share another API request here. So this is the API request that is actually being sent to the inference server. So all of you can see that the prompt is encrypted, then it's encoded into base 64 version of that. And then there are some model generation parameters that are being sent, like what is the maximum number of tokens that you want, what is the temperature. So if we send this request, what happens is the request would be captured by server. It will decrypt this encrypted prompt, understand what the data was provided in prompt, and then generate a response which is based on this encrypted. And then once it has generated the response, it will encrypt the response back again and send it with client. So even if someone captures your response, they won't be able to decrypt this response because they don't have the shared key that is established between the client and the server. Coming back to the slides. Sorry, come on. Yeah. So what are the future directions for this? So one of the possible concepts, and many companies are trying to implement this today, is the full homomorphic encryption. So in the POC that I showed, there is a single point of vulnerability, which is the shared key. So if the shared key is exposed, then anyone can easily decrypt the response. So to avoid that, we can use full homomorphic encryption. What happens in here is the prompt is encrypted, it is sent to server, but server doesn't decrypt it. It generates the response based on the encrypted prompt itself, and it again encrypts the response and sends it back to the client. So the decryption happens only at the client's device level. It is not decrypted anywhere on the network or at rest. But the problem with this full homomorphic encryption approach is that it is 5,000 times slower than the current inferencing. So till computationally, we are not there yet, but I think that's the future where all of us want to go to. Another is the MCP layer encryption. As Aman mentioned, so MCP is now becoming the de facto standard for interacting with the systems which are outside. For example, you can consider like you are an employee or a business owner who wants to fetch the data for sales pipeline for this quarter. And that is a confidential data that nobody should get access to easily. So what you do is, let's say your sales data is stored in a system like Salesforce, and you integrate Salesforce's MCP server with your AI agent, right? So you ask it like, give me data about my sales pipeline for Q3. So it will provide you with maybe the name of customer, what was the deal size that happened, what was the deal value, and all of that would be written by MCP server in plain text. So exposing this kind of information would be a big security threat for businesses. So we also have to think in the direction how we can apply encryption in the MCP layer also, so that only the AI inference server and the MCP are able to decrypt whatever request and response are being shared. The code for this is available on GitHub, and this is like POC code. And me being from application development background, I use Claude to implement most of these pieces. But yeah, you guys being expert, I would request you to take a look and maybe take this forward. Now coming to the deep dive part. So let me share this. I can maybe minimize this. Yep. So our application is simple. It's a client and server, a two-layer application. What's unique about this? The unique idea here is that we are using the dual encryption. So as you can see in the this diagram, the client side has a Python application which encrypts the request. Whenever user types a prompt, it encrypts the request, and then before sending it over the network, it uses TLS 1.3 channel to re-encrypt the request and transit. So it's hard to break. On the server side, we have the modified llama.cpp server, and each of these has then different components. Like on the client side, we have Python application, the encryption manager, which utilizes PyCryptodome library, as I mentioned. For decryption, we are using the OpenSSL library on server side, which is in C++. And there are HTTP clients who does the job of sending on the network and establishing SSL connection. So there are very clear trust boundaries that are established for each level of interaction. So client to network is the application level encryption. So this encrypted, the prompt that user typed never leaves user's device without being encrypted. In the network to server level, we have TLS encryption, and since the prompt is already encrypted, nobody can decrypt it and extract the actual value. On the server side, we have like the trusted memory space where only the decrypted version of the prompt is available. And that trusted memory space is basically your variables in which the decrypted value of the application is, decrypted value of the prompt is stored. So it's not living your application, and since it's in trusted memory space, what would happen? So if you shut down the server application, all of the data would be wiped out, since all of that is in a random access memory. Now coming to the component overview part of this project. So in client, we have three different components. One is user interface layer, which has like CLI application, the Python API, and the configuration manager. In configuration manager, you can manage the configuration of like which server you want to connect, which port do you want to connect, what is the maximum token size that you want to have. All of that can be configured in config.python. At the security layer, we have encryption manager. We have support for key management. So right now it's like hard-coded key. And then we have support for input validation as well. Then we have communication layer at the client side, which is basically the handling of HTTP request and response. Then in the server side, we have these components, a similar structure, I would say, but just like network layer comes in first, which decodes the base 64 version of your prompt, and then sends it to encryption manager for decryption. Decrypts it using the initialization vector that was sent in the request and the shared key that it already had. And then once it's decrypted, it is sent to llama.cpp integration, which is modified version of the llama.cpp server to support encryption and decryption. The request processing happens, response is generated, and then response is re-encrypted by initializing a random initialization vector again, and the response is sent back to the client. If you want to see the data flow for the application, so user input, so let's say user asks a question like what is machine learning. So step one is the prompt is entered by user, then the client side encryption happens where we are using the AES-256 CBC encryption. As I mentioned earlier, the initialization vector is randomly generated for each request. We are also using PKCS7 padding to make sure that in the CBC, we are able to encrypt and decrypt it properly. And then we are finally base64 encoding the data to reduce the size of the request. The encrypted data plus initialization vector, which can look like the example output, is then sent over the network. On the network side, the JSON request is created. This is the format of the JSON request where you provide encrypted prompt, the initialization vector, max tokens, and the model configuration. Then a TLS connection is established with the server, and the request is sent over the network. Step 3 is the request comes to server side. The TLS decryption happens. Server can validate. So if we have something like mutual TLS authentication in place, the server can validate that the client is authentic, like it's a validated client. And then the server can extract the JSON payload and validate the request structure. Then utilizing OpenSSL, you can decrypt the request using the AES-256 CBC decryption, and the PKCS7 padding is removed. And what you get is plain text that is then stored in trusted memory space. So all of this code is present in the integration folder here. And the server is like present in this encrypted llama, encrypted server.cpp, and an executable is also generated here. We are using CMake as the build system to generate the encrypted llama.cpp server. And then coming to step 4, what llama.cpp inference engine does is it produces the token, it does a model forward pass, it generates the response, detokenizes the response, and the plain text response is generated. But since the plain text response is only stored in the variable, it's just a value assigned to a variable which is in the trusted memory application space. It's not yet sent over a network or logged anywhere in any of the exposure points like your logging systems or your monitoring or auditing systems. Then the server re-encrypts the response back, and then the constructs a JSON request and sends it back over the network. Again, at the network level, the encryption is in place for HTTPS TLS 1.3. So the response is generated securely, like transported securely to the client. At client side, it decrypts the response and then presents it to the user. So the security properties that are maintained here are like no plaintext exposure in network, on server, or the plaintext existence is in trusted memory space only. There is an independent initialization vector that is created for each request, and even for response. For response as well, server would generate a new initialization vector and encrypt the response and send it back. So there is end-to-end encryption with defense in depth. Then all of this documentation regarding the detailed encryption protocol flow is also available on the GitHub repository. This is the component architecture. Now coming to the interesting part where how you can utilize this in the production application. So I was mentioning multiple times that we have a shared secret key that's hard-coded as of now. In production, what you can do is you can have an HSM which will store the key. For key generation, you can use a key management service that can generate a key for a particular session. Then utilizing that key, client can encrypt and server can decrypt the response. And once the session is closed, so for example, your particular session is closed, like you ended the chat, at that point, the key would be destroyed from the HMS. So even if someone gets the encrypted conversation and tries to decrypt it, they wouldn't be able to do so because your conversation, the key that was used for encryption has already been destroyed. So that's how you can utilize this in production, and all of that is mentioned here in the key management encryption key architecture. So this is the current implementation, and this is the production architecture. Cool. Now coming back to slide, I think that was it from my our side. And if you want to connect with us, talk more on this concept, here are our LinkedIn profile URLs. Yes.
It's a great work. I see that you guys use a lot of confidential computing primitives there and trusted execution environments. But what I don't see is that what memory encryption engine do you guys use? Because do you guys talk about trusted memory space, encrypted memory? But is it all software-based encryption, or because HSM will not help you for runtime memory encryption, you would need, I don't know, Intel SGX, AMD SEV, or ARM CCA. But I see none of them because user, the prompt owner basically needs to have some evidence that all the protocol you described is followed. Because server can easily fake all these things and generate, maybe or there will be a lot of other man-in-the-middle servers. So how do you make sure, or would you make sure that, is it on the roadmap maybe, that using actual hardware, secure hardware underlying, or?
So as of now, we recommend using on-premise inference engines rather than using publicly available inference APIs. So that's the easiest way to achieve this. If you have confidential data that shouldn't be exposed even via trusted memory space, then your only option as of now is to use your on-premise inference engines, maybe utilize inference engines like VLLM, NMVLLM, and host it on your premise. Don't use any vendor-provided inference APIs.
So the threat model would be then you're trying to protect these prompts and content against the insider threat within the company on-premise servers.
Yes.
And that would work then. Because it's not like you're talking about remote servers, but local server security hardening you're doing.
You're absolutely
Very
right.
interesting. Very
yes.
interesting.
It's for the internal threat actors. Yes.
Are there any other questions? If not, so let me think. Or one more question.
Yeah.
How do you prevent LLM misuse, basically, since you're not logging any prompts? How can you find out that somebody is misusing the LLM for incorrect ways?
Yeah, so I think right off the top of my mind, I can think of two things. One is eventually using full homomorphic encryptions. That way, we'll at least have some guardrails around it. Second way is in the inference engine itself, you have one another, a call to a guardrail model, like a IBM Granite Guardian model that can tell you, okay, don't process this or process it. Or you can also have it integrated with MCP. It's again in future direction. If we can integrate MCP, it can make multiple inference calls. First, it can understand, okay, this is a valid request. This is not misusing the actual model. Then only proceed to next iterations. We wanted to demonstrate MCP part, but we couldn't. But that's on in future directions how we can integrate MCP and have a full multi inference call or a agent architecture as well with this end-to-end encryption approach.
Yeah, but these are only preventions, so you cannot actually monitor, and you don't have any evidence what actually users are sending to the LLM, so you have no evidence on what actually might be malicious, right?
Yeah.
I just thought that it's the point of the talk, that you don't see the data.
Yeah.
You can't log the data because that's the problem. The companies just trying to monitor what you are doing.
Correct.
And this is the way how to do it. It will be same with homomorphic encryption because it's my take. I am no expert, but
No, you are
my take
absolutely
is that you can't, because it's the user thing, and you can do preventions, firewalls, applications like this, but you cannot monitor it back. You shouldn't
Just
as a company.
Just think of it as like we are talking on a platform, and we don't want our chats to be monitored at all, right? And that's expected behavior. We don't want to monitor or log anything.
Yeah, I understand that, but this whole system is for like internal purposes, and you're trying to prevent internal threat actors, right?
Yeah, it can be used in, so if you think in terms of customers, it can be used in healthcare domain and defense, where the data or the kind of information that you are asking or the response that is being generated, you don't want that to be leaked anywhere.
Yeah. But
And if like in future, if this becomes a standard, everybody implements similar system, maybe in future you can interact with OpenAI with using some HSM keys, and it's again end-to-end encrypted with, even while you are talking to ChatGPT, it's again end-to-end encrypted. That could be a future thing, but I don't see like all vendors coming to a single standard and adopting it. So,
yeah, thank you.
Yeah, one more question. Thank you for a really interesting topic. I'm not so good in cryptography, but I have a little bit of side question, more practical. So eventually I didn't get where you store context of conversation, right? Because we saw during the demo just a single question being posted and eventually reply coming back. So for me, from practical kind of point of view, it's interesting how it's possible with current approach eventually to restore prior conversations, right, and context. And the second question is related to performance, right? Because eventually if you keep everything on the client side, context may grow, and encryption of that will take more and more time. So have you done any kind of performance tests to find like a maximum context window where it's still kind of usable?
absolutely, fantastic questions. Yeah, we have not done benchmarking as of now. It was just like initial POC for us. We were trying to establish a baseline. Okay, can we do this? Yeah, we can. Like it's like a concept for us as of now. And I understand like the conversations. I believe it will be part of MCP protocol once we have enabled encryption with the MCP. That way it can also like dual layer encryption at data at rest as well. This only talked about dual layer encryption for data in transit, but we also need to do dual layer encryption for data at rest. Then we'll be able to like include conversations too.
Yeah, and that's actually a question, because you said that you are like decommissioning like keys, right, and so certificates which you use during a session. So you are like closing the door eventually to restore a context. So will be there any different approach eventually to encrypting data and storing it at rest? So like
No, I think
before closing connection, maybe like.
Yeah, for context, I think it would be like if you want to continue the conversation history, then we need to, like as Aman mentioned, we need to encrypt that at rest and store it, and then we can fetch it. But for that, I think we need another secure key, which would be stored somewhere else.
Yeah, I think that.
And for performance benchmark, if you check the GitHub repository, there is a script there using which you can evaluate the performance.
Thank you.
One last question.
Thank you. Just sort of bouncing off the question that was raised by the gentleman next to me before, I guess sort of thinking it through, couldn't this, if it's designed to prevent internal threat actors, this solution as you proposed it could also be a really good way for a threat actor to sort of hide their tracks, because you could, if I was an internal threat actor and I found a way to use this system, I could use it to say, get an AI agent to say, the entire source code for this product, can you please export it to XYZ location, and it would be completely invisible effectively. Is that like a fair statement of a potential risk?
I would say that what your AI agent is capable of and what capabilities you provide is up to the developer of the AI agent. For example, your AI agent can even do RM, RF, and delete all of your system, right? That is possible today. It can do that. So the only piece that we can do there is have like guardrail models in place that would avoid AI agent from taking those kind of actions. But that is, I think, something else that is out of context of this topic.
Yeah, that is still applicable whether you do
Yeah.
encrypt or do
Yeah.
not encrypt. So yeah.
Okay, so thank you very much, guys. Very interesting presentation and big applause. Thank you.
Thank you.
Thank you.